Today I'm returning to a problem that I started and mostly solved a little while ago. It was one that was submitted by a viewer. I'll read out the original problem. It says a function s of x returns a minimum positive integer such that its multiplication of digits equals x. If there is no such integer, the value is 0. From positive integers less than 100, find an argument a such that s of a is maximized. So I did that in a previous video. I actually don't remember what the answer is, but the viewer had a follow-up question, which was to do this rather than for integers less than 100, do it for integers less than 10,000. So I had a few thoughts about how I might approach this. Another viewer commented on the original video saying that there's an algorithm for how to figure this out. I don't think what I'm going to do here is exactly designing an algorithm, but I do want to kind of figure out a little bit more about the structure of how this works and see if I can make some progress on finding the maximum of this value for integers less than 10,000. So let me summarize what's going on in the problem. So f of x is going to be equal to an integer y, and I'll write y when I write something like this, a, b, c, and so on, up to, I'll just arbitrarily say k. Then it's applied that a, b, c, and so on, these are the digits of y, and the product of these things is equal to x, and this is the smallest such integer with that property, positive integer. If there is no value, if there is no integer such that the product of the digits is equal to x, then we say s of x is equal to 0. So I had written out a few values of s of x in my previous video. So for the integers up to 9, it's just itself like this. For 10, I guess it'll be 25. Right? 2 times 5 is 10. For 11, it'll be 0. For any number which is prime, but at least 2 digits, the answer is going to be 0. And in fact, for any multiple of a prime, which is at least, if the prime is at least 2 digits, any multiple of that prime, s of x, will be equal to 0. Okay, so the way I want to try to approach this question is to just construct an integer. So basically just start writing down digits such that the product of these digits is less than 10,000. I want to make sure that the number that I get here is a legal output of the function, and then I want to try and maximize that. So there are certain properties that the output of this function have to satisfy. For example, the numbers, as we go from left to right, the sequence of digits we put in here has to be non-decreasing. And the reason for that is because let's say x is equal to 5 times 4 times 5. Then x is also equal to 4 times 5 times 5. And so in this case, s of x has to be less than or equal to, it can't possibly be greater than 455. Okay, so if I ever have a sequence of digits where it decreases in going from one to the other, I can just interchange those and the product is the same. So the output, any legal output of the function s of x has to have the digits non-decreasing. The other thing that I realized in my previous video is that if I have an output which is something like 2, 2, 7, Well, this will not be legal because this can be replaced with 47. So the way I want to start this video is basically by coming up with all of the ways that I can replace some number with something smaller, such that the product of the digits is the same. And I'm hoping to then, from that, sort of build, I want to just try and construct the largest possible number that will work. Okay, so I can't possibly have two 2's in the result because that can be replaced with a 4. I can't have a 2 times 3 because that can be replaced with a 6. I can't have a 2 times 4 because that can be replaced with an 8. I can't have a 3 times 4 because that can be replaced with 3 times 2 times 2, which is the same as 2 times 6. Right, and I can't decompose this in any way that gives me something less than 26. What about 2 times 8? That should be fine, right? The only other way I could rearrange that would be 4 times 4, and that's 44 is bigger than 28. What about 6 times 8? Well, hold on, I'm skipping ahead here. 4 times 6. Well, this is the same as 2 times 2 times 2 times 3. I can replace this with 38. Okay, so I can't have a 4 and a 6 because that can be replaced with 38, which is smaller. Do I have to keep going with powers of 2 here? Let's try 4 times 8. So this is 2 times 2 times 2 times 2 times 2, right? I think that's okay. 4 times 8 is okay. Because if I take a 2 out of this and put it in there, well, it's the same. 8 times 4, 4 times 8, always gets rearranged to 48. And if I take a 2 out of this and put it in there, I no longer have a 2-digit number. So 48 is okay. What about other things with a 6? What about 36? 3 times 6. This is the same as 3 times 3 times 2, which is 29. Okay, so I cannot have a 36 or a 3 and a 6. What about other things with a 9 in them? 4 times 9. This is 2 times 3 times 2 times 3. So that could be replaced with 66, but that's not smaller. So 4 times 9 is okay. But this does show that 66 does not work. 66 can be replaced with 49. Okay. What about 3 times 8 should be fine. 6 times 8 should be fine, I think. And if I have a 5 or a 7, Those are prime. There's no way you'll be able to replace anything with that. What about something that has a 9 in it? 19 is fine. No, sorry, there will not be a 1. You'll never have a 1 in the output because that doesn't affect the product. Just eliminate the 1 and the number gets smaller. So 29, well, that's here. That's not going to be replaced with something. 39 is okay. 49. I think that's fine. 59 is fine. 69, I didn't try 69. I think this should be fine as well. So how do I go about using, let's assume for now that all of the possible replacements are here. So we also know that there will not be a 1 or a 0 in the result. How do I make an integer using these, forcing these replacements? Make an integer as large as possible so that the product is less than 10,000. What is S of 10,000? So this will be 2 to the 4 is the same as 2 times 8. So these are all being multiplied. So S of 10,000 would be 2 times 5, 2, 5, 5, 5, 5, 5, 8. Okay, you know what? I think that I did something similar in my previous, in my attempt at the easier question. And I sort of just started with, let's fix the number of digits and then try and maximize a legal output of that size. So let's start with 5 digits. 1, 2, 3, 4, 5. Well, the largest number I can put here is 99999. Is that product less than 10,000? No, it's 59,000. Okay, so this has to be a lot smaller. 10 to the 4. So I could put 66666 here. This gives me a number. When I multiply this out, it gives me something less than 10,000. But 6, 6 gets replaced with 4 and 9. So 4 and 9. Replace these with 4 and 9. And then this gets rearranged to 4, 4, 6, 9, 9. I think I missed one of my possible replacements here, right? 4 times 4 should get replaced with 2 times 8. Two, 6, 8, 9, 9. So 2 and a 6 is fine. 6 and 8 is fine. 6 and 9 is fine. 2 and 9. And what is this? When I multiply these together, what do I get? So S of 7, 7, 7, 6, I believe, if I did this correctly, is 2, 6, 8, 9, 9. Can we make something bigger? Well, if I change this to 3, 6, 8, 9, 9, 3 times 6 gets replaced with 29. And this product is, this product is now greater than 10,000. This is equal to 11,664. So I guess one of the ideas is that you probably want a lot of primes, because a lot of primes you're not going to be able to replace. Well, do you want a lot of primes? Because, if I fill it with 7s, I might want something that multiplies to something greater than 7, but it's 2 digits. So 2 times 5, for example. Like one way of thinking about this problem is start with any legal output of the function. So for example, 2, 6, 8, 9, 9. And do an operation on this where I, replace one number with another, or split this into like a 2 times 3 and then replace the 2 or the 3 with something else, such that it gets bigger and is also a legal output. And then just do that as many times as possible, such that the product is always less than 10,000. But that doesn't guarantee you end up at the maximum possible. Okay, how about we stick with the 5-digit plan, but I put a 3 as the first number. Then the next number has to be 3 or larger. It can't be a 3 itself. Can it be a 4? No, because that can be replaced with 26, right? 3 times 4 was in my list of things I can't use, 26. So the next number would have to be at least a 5. So this is, what is the product of this? Well less than 10,000. Okay. So we're looking for a 5-digit number. Okay, so this is too big because this product gives me almost 20,000. So if I replace this put an 8 here. That's also too big. Okay, so if I multiply these digits together, I get 7203, which is less than 10,000. Can probably replace one of these with an 8 and still be within the right range. Yeah. Does this, is a 3 and an 8 legal? It's not on my list. How could I split this up? That's 2 times 4. Yeah, I don't think this can be. And what if I replace that with a 9? Yeah, I can put a 9 here. This is still less than 10,000. I'm not going to write what the output is at this point. This is less than 10,000. But I cannot replace the 7 with an 8. But if I replace this with an 8 and this with a 6, wait, let's go back. 7 and 7. If I replace with a 7 and a 6, this overall number gets smaller. Something else I'm realizing now, I wonder if this will help in any way. N squared compared to n minus 1 times n plus 1. Well, the right-hand side turns into n squared minus 1, right? So if I have 2 digits here that are the same, if I replace one with something higher and the other with something lower, the product goes down. So if I replace this with an 8 and an 8, right? 3, 7, 7, 8, 9. Oh, but that product is greater than 10,000. Starting to think I want to look at 6-digit numbers now. So I can't even fill it. If I fill it all with 5s, that product is greater than 10,000. So the first number cannot be a 5. Let's try this. Okay, so I can't have a 5 here. I could put a 4, but that would a 44 gets replaced with a 28. So I'm going to put a 3 in the first digit. So if I do this, this product is less than 10,000. So certainly the number I'm looking for here is, as an output, as a legal output, is at least 6 digits. Didn't have to waste my time with all this 5-digit stuff. Okay, but if I replace this, if I replace a 5 with a 7, it breaks it. It goes above 10,000. What about if I multiply by 6? No, it doesn't work either. Okay, so I want to make this number bigger such that the product of the digits is still less than 10,000. And I don't know if that's possible, but let me see if I can come up with an argument for why it's not possible. Like, if I replace a 5 with a 6, it gets too big. But if I replace a 5 with a 6 and another 5 with a 4, right, this is equal to 9,000, this product. But this is not, this output is not legal because I can rearrange things here. The 3 times 4 can be arranged into 2 times 6 times 6 times 5 times 5 times 5. And the output is 2, 5, 5, 5, 6, 6. And 66 is the same as 4 times 4 times 9 times 9. Wait. Is 66 is the same as 4 and 9. So this becomes 2, 4, 5, 5, 5, 9. Would it be possible to do anything with 7 digits? If I have a 2, then the next number has to be at least a 5. Otherwise it can be combined with the 2. And then, if things are non-decreasing, this is certainly a lot larger than 10,000. Okay, so I have a 6-digit number, which is a legal output. Product is less than 10,000. What if I replace a 3 and a 5 with a 4 and a 4? Well, but 4 and 4 is the same as 2 and 8. So it's gotten smaller. Okay, I can't replace a 5 with a 7. Can I replace a 5 with a 6? Won't help. I find it hard to believe that I'll be able to find a larger number here that works, because if I replace a single 5 with a 6, the product goes over 10,000. If I replace the 3 with a 4, the product goes over 10,000. And then if I want to make this number bigger in any way, like something's got to get bigger, and in return something else has to get smaller. But if I replace a 5 with a 4, 3 times 4 can be written as 2 times 6. And so the leading digit of 2 will be less than 3, and the whole number will get smaller, in fact, rather than bigger. I don't want to spend too much time going through this. This answer may not be correct. This may not be the largest output for inputs less than 10,000, but I don't see a way of making sort of a single manipulation to this. I don't see a way of making a single manipulation to this with a corresponding compensation in another digit such that the product stays less than 10,000. So, I mean, maybe don't consider this the correct answer, but consider it my best attempt at maximizing the output. So I'm saying that 9375. Wait a minute. I know. If I fill it all in with 4s, this product is less than 10,000, right? Yeah, it's only 4,000 or so. But a 4 and a 4 can be replaced with a 2 and an 8. So it's the same as 2, 4, 4, 4, 4, 8. And a lot of these other ones can be replaced as well. So like this certainly will not work. Yeah, I'm going to stick with this for now. You know, again, I don't know if it's completely correct. If someone finds an input to this function that has a larger output here, where the input is less than 10,000, you know, leave it in a comment. But I'd be interested to hear from one of my other viewers who said that they developed an algorithm for how to sort of figure out what these what this number is. It'd be really cool to see what that is. I'm going to leave it here though. I don't want to go on for a huge long time. But this was a really cool problem overall. Thanks for watching.